The first part of Chapter 4 will include several sections that cover the nomenclature of organic compounds. Nomenclature is simply the naming of organic compounds. And because the nomenclature for each different type of molecule, functional group, is spread throughout the book, it makes more sense to chunk it all into one unit. So that's what we're going to do. We're going to look at 4.1 and 4.2 in this particular lecture, but then the rest of our nomenclature unit will cover sections 7.2 to 22.2. These are just individual sections from a chapter. So 4.1 and 4.2, 4.1 and 4.2 will be part 1 of our nomenclature unit, and the rest will be part 2. So let's begin with section 4.1, which is just an introduction to alkanes, and you're already familiar with the general structure for a saturated hydrocarbon, or the general formula for a saturated hydrocarbon. A hydrocarbon is anything that contains only hydrogen and carbon, and saturated simply means it has the maximum amount of hydrogens. So we saw in section 14.16 that a degree of unsaturation counts as a pi bond or a ring. Well, saturated hydrocarbons technically do not contain any pi bonds. For example, like ethane, C6 or C2H6. This follows the formula C to the N, H to the 2N plus 2. Unsaturated hydrocarbons contain pi bonds. So that would be 1 degree of unsaturation. That would be 2 degrees of unsaturation. And for benzene, we have 1, 2, 3 pi bonds and a ring. So there's 4 degrees of unsaturation. 1, 2, and 4 degrees of unsaturation. Whenever we name hydrocarbons, we use the suffix ane. Now, earlier in the semester, I'd asked you to familiarize yourselves with the names of the straight chain hydrocarbons, and this is where we need to know that. So make sure you know the names for the straight chain hydrocarbons containing carbons 1 through 10 in their chain length. All right, so with that said, that's a simple introduction to alkanes, and we're going to name them. In section 4.2, we're going to dig deeper into the naming system and look at more complex alkanes than just the straight chains. But we need that straight chain alkane nomenclature as a basis to do section 4.2. So if you haven't done that, if you haven't learned them already, go back and look at the names and formulas for the straight chain hydrocarbons for 1 through 10 carbons. All right. So organic compounds have common names and they have systematic names. We're going to focus on their systematic names, although we may use common names here and there. The systematic naming system is called the IUPAC system. It's the International Union of Pure and Applied Chemistry. You don't need to have that memorized, but that's just what it's called. When we name any organic molecule, we have a very general naming format. And below here, we have that system. We're going to focus on the parent stem, then we'll move to adding prefixes. And once we learn the parent stem and how to add prefixes for the branches, then we'll move on to alkenes, alkynes, and we'll look at other functional groups. So this is where we're starting. So a name always includes a parent stem, prefixes, the stereoisomerism, carbon-carbon bond type, and any high priority suffixes. And this is generally, this template that you see here is the format in order of how we construct the name of an organic compound. So if you have to refer back to this, just remember this is sort of a generic template for every name. We're going to be starting with the parent stem. All right, so in order to name an alkane, the simplest of the organic molecules, the basic steps are listed. We have to name that parent chain. That's the parent stem that I mentioned on the previous slide. We're going to identify and name substituents. Those are your branching groups. We're going to number the parent chain, and we're going to call those numbers locants. And it's just a number that assigns a position to each of the substituents or branches. And we always give our first substituent the lowest possible number, but we'll come back to that. And finally, we're going to list all of our numbered substituents before the parent name in alphabetical order, and we're going to plug everything into that template that I showed you on the previous slide. So step one, we have to identify the parent chain. And the parent chain is simply the longest consecutive chain of carbons in the molecule. Now, in order to name the parent chain, you're going to need to know these parent names, like carbons 1 through 10. We have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. These will be the names of the parent chains. And because we're dealing with alkanes, they will all end in an A and E. So, if we look at our first example, we want to name the parent chain. We look for the longest consecutive chain of carbons. And you could try a lot of different options here. You don't always see it on the first shot. You might try, all right, here's 1, 2, 3, 4, 5, 6. Let's see. Let's say you chose that. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's 8. We have, if we get rid of that one, we could try another one. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's longer, so that's an option. Let's check another one. 1, 2, 3, 4, 5, 6, 7, 8. So that one there is 8. Still not the best option. It looks like this carbon chain here is the longest consecutive chain of carbons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons in a consecutive chain. They don't have to be straight left to right. Visually, it doesn't matter. Remember, molecules exist in three-dimensional space. They can be rotated, turned. Single bonds can be rotated, right? So the way it looks can be a little bit misleading. So just count the consecutive carbons. So we've identified that our parent chain has 9 carbons. So we come to 9 and we say, oh, the parent chain is called nonane. And then that's our parent stem in that template that we saw a few slides back. If there's more than one possible parent chain, you choose the one with the most substituents. So a substituent is just a branch. It's a branch off of the parent chain. All right, so if we want to identify the parent name for the compound below, right, well, we see we have 1, 2, 3, 4, 5, 6, 7. And let's look at the other option, 1, 2, 3, 4, 5, 6, 7. make sure you see the difference here between the parent chain. This one's split off to the right here. This one split off to the left. All right. So the difference is that our carbon, let's look at each carbon in our chain. 1, 2, 3, 4, 5, 6, 7. They both have 7. Now the rule to determine which is the correct parent name is which one has the most substituents or branches. So I see a branch here off of the main chain, I see a branch here, and I see a branch here. Branch and a branch. So we have 3 branches or 3 substituents versus parent chain that has 2 substituents. Therefore, this is your correct parent chain. And a parent chain with 7 carbons is called heptane. All right. If the parent chain happens to be cyclic, meaning the longest consecutive chain of carbons is in a ring, we use the prefix cyclo at the beginning of the parent name. So for example, we have 1, 2, 3 carbons, so that's propane. Because it's in a ring, we say it's cyclopropane. We have 1, 2, 3, 4 carbons in a ring. We call it cyclobutane. Bute is for 4. And if we have 1, 2, 3, 4, 5 carbons, that prefix is pent, so we call that cyclopentane. All right, so what I'd like you to do is pause the video and try to identify the parent chain for each of the following molecules. When you come back, I'll give you the answers. All right, hopefully you were able to give this a shot. Let's take a look. In our first example, it should be pretty straightforward. The longest carbon chain, we have 1, 2, 3, 4, 5, 6. So the parent chain is called hexane. Hex is for 6. And let's look at the next one. We have 1, 2, 3, 4, 5, 6, 7. You can only count the number of carbons in the ring. Do not count the carbons inside and outside. It's only inside the ring. So that's 7. That's cycloheptane. Hept is for 7. Don't mix these two up. Hex and hept are often confusing. All right, let's look at the next one. I think you can clearly see we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That is, hold on. That's one option. So let's circle that. So here's one, that was 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's look at another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got one that has 10. So in this case, our longest chain would be called decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's decane, and dec is for 10. The next step in naming an alkane is to identify the substituents. So remember, a substituent is simply a branch off of the main chain. So our parent chain is the longest consecutive chain. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a form of decane. But let's look for the branches coming off of this chain. 1, 2, 3 branches. And we name these branches by counting the carbons. So in our first branch, there's 1 carbon, 2 carbons. And if we refer to table 4.2, a 2-carbon branch is an ethyl. So all of these are considered to be alkyl groups. See the YL, we call that an ethyl group. So for each substituent name, you change the N to YL instead of an A and E. Substituents are alkyl groups, so that is an ethyl group. Down here we have 1, 2, 3. That group is called a propyl group. And for our last one, we just have a single carbon branch. That's called a methyl group. So all of the branches have the same names as our carbon chains 1 through 10, but the only difference is we just add a YL to the end of each alkyl substituent name. All right. We said that a ring can be a parent chain, but it can also be a substituent. So rings can be parent chains or substituents depending on the number of carbons. So if the longest parent chain is in the ring, or if the longest chain is part of the ring, then the ring is the parent. However, if the longest consecutive chain is outside of the ring, right, then that chain is the parent and the ring is the substituent. So when a ring is a substituent, we just say that it's a in this case we have a 1, 2, 3 carbon ring. It would be a cyclopropyl substituent. Remember, for all alkyl groups we had the YL. And our parent was butane because we have 1, 2, 3, 4 carbons in the longest consecutive chain. For the next example, I'd like you to stop the video and pause the video and try to identify and name all of the substituents in the following compounds. So that means you're going to have to find the parent chain first. So when you come back, I'll give you the answer. All right, hopefully everyone was able to give it a shot. So we have a couple options here for identifying the longest parent chain. We could say 1, 2, 3, 4, 5, 6, 7, 8, 9. That gives us 1, 2, 3 substituents. Or I could have done 1, 2, 3, 4, 5, 6, 7, 8, 9. That is also a carbon chain with 9 carbons. But this one has 1, 2, 3, 4 substituents. So remember, when we have an option of 2 carbon chains of the same length, you choose the one with the greater number of substituents, and that will be the correct parent chain. So now that we know that our parent chain has 9 carbons, that's nonane, let's look at the substituents. A 1 carbon substituent is a methyl group, or a methyl substituent. A 2 carbon substituent, see 1, 2 carbons in the branch, is an ethyl group. For the next one, we have 1, 2, 3 carbons on our branch. That's a propyl group. And again, we have a 1 carbon branch that's a methyl group. right. The complex substituents are basically those that are not just straight chain branches. So they have separate naming and numbering systems. You're not responsible for the IUPAC naming and numbering system for these complex substituents. However, you must know the common names for the following: the isopropyl group, the tert-butyl, the phenyl, the benzyl, and the allyl. Now, these are not the only complex substituents. There are dozens of complex substituents with common names and IUPAC names. But these are the common ones that we're going to see most often. So these are the ones that I need you to know. There's 1, 2, 3, 4, 5 of these. And you know the common name only for these substituents. All right. Next, we want to number the parent chain and assign a locant to each substituent. So after we identify the parent chain, we identify the substituent, we're going to number the parent chain to give each substituent a number. And that's all that a locant is. It's a number that identifies the position of that substituent. So the guidelines when numbering: if only one substituent is present, then you number the parent chain so that substituent gets the lowest number. For example, we have a carbon chain of 7 carbons. I could start numbering from the left, and we see that my substituent on carbon number 2, that methyl group, would have a 2 position. If I started numbering from the right, my substituent, my methyl group, would get a 6. So a 2 beats a 6. So this is the correct numbering system, giving the substituent the lowest possible locant number. If multiple substituents are present, you're going to number the parent chain so that the first substituent gets the lowest possible number. All right, so we have multiple substituents. I can start numbering from the left. So 1, 2, 3, 4, 5, 6, 7. That gives me a methyl group, my first group at a 2, and my second 2 methyl groups. We give them individual locants, so that's 5, 5. If I started numbering from the right, my first set of substituents would be my 2 methyls at the 3 and 3, and then we have our last methyl at the 6. So remember, when multiple substituents are present, we want to give the first substituent the lowest possible number. Therefore, numbering from the left puts that methyl group at a 2, and a 2 beats the 3 if I started numbering in the other direction. Now, if you've got a tie where the first substituent gets the same number, if you have 2 options, then we just go to the second substituent. We want to put the second locant on the lowest possible number. So for example, if we have a 7 carbon chain, and if I start numbering from the right, that gives me my first substituent at a 2, second substituent at a 3, third substituent at a 6. So that's a 2, 3, 6. And if I started numbering from the left here, well, my first and last substituents are at a 2 and a 6. That's the same as my first system. However, my second substituent that I encounter, numbering 1, 2, 3, 4, 5, would get the 5 position. So a 3 beats a 5. So this is the correct numbering system, starting from the right there. If there's no other tiebreaker, we assign the lowest possible number for the substituents alphabetically. So for example, we've got a chloro group and a bromo group. We're going to learn more about naming alkyl halides later. But that's a chloro versus a bromo. So if I started numbering with my carbon attached to the bromine as number 1, okay, I get a 1 bromo, versus if I started over here with the carbon attached to the chlorine, if I called that number 1, that would be 1 chloro. So the substituent with the lowest number, right, should be alphabetical order now because it's a 1 and a 1. So bromo B beats C. So this is the correct numbering system. And when you're dealing with cycloalkanes, all the same rules apply. So let's look at two options. I could start numbering here on the left, call that 1, 2, 3. My first substituent contains 2 methyls, so that's a 1, 1. Remember, if it's the same type of substituent on the same carbon, we have to repeat it, so that's a 1, 1. It's very important to note that. We have 2 methyls, so that's 1, 1. Now, if I started numbering from the other direction, my first methyl gets a 1, but then the second 2 substituents, that's a 3, 3. So a 1, 1, 3 beats a 1, 3, 3. And the name of this happens to be 1, 1, 3 trimethyl cyclohexane. Okay, the substituents on cycloalkanes can be ranked alphabetically when choosing where to begin numbering. Again, so let's say we have the following compound and we want to choose the correct numbering system. If I went counterclockwise around the ring, then I get the 1, 2, 3, 4, 5. That puts my first substituent on, I have a 1, so that would be a 1 ethyl. And then I have a 3 methyl. The other option would be a 1 ethyl and a 4 methyl. Clearly, that's not the right numbering system. Or I could do a 1 methyl, 3 ethyl. So we have a tie between these two, but the correct numbering system, again, we'll put the lowest substituent alphabetically. So E comes before M. That's why this is the correct numbering system when we have a tie. The final step in naming alkanes is to put the name together by listing the numbered substituents before the parent name. Okay, this is that on that template we had our parent name and then we had the prefixes for the number substituents. And we're going to do all of this in alphabetical order. So you're going to need an additional prefix if there are multiple substituents of the same type. That typo should be tetra. For example, in the previous slide, we saw there were multiple methyl groups. That would be, if you had 2 methyls, it would be a dimethyl. If you had 3 methyls, it would be trimethyl. Do not use these prefixes for alphabetical purposes unless don't use these prefixes alphabetically unless we're dealing with an iso. So we had that isopropyl group. This is the only exception. So when you see an isopropyl group, we are going to consider the I alphabetically. Everything else, the di, tri, tetra, all right, we don't include those prefixes alphabetically. Another example. So an ethyl would come before a dimethyl, right? We are ignoring that di for the dimethyl. That prefix is not used alphabetically. All right, when we put the name together, hyphens separate numbers from letters, and commas separate numbers from each other. So let's say we wanted to name the following molecule, right, and put it all together. first we have to identify the parent chain. Well, the longest consecutive chain is the one that's in the ring. So it's 6 carbons in the ring, so we call that cyclohexane. Now let's look at each of the substituents. This is a common substituent, or a complex substituent, and the common name is a tert-butyl. Tert-butyl. We have an ethyl. We have methyls. Okay, so we've numbered the chain, or we've identified the parent chain. We've identified our substituents. Now we have to number the parent chain. So we have a lot of options here. We could number the parent chain starting at the top, in which my first substituent, right, would start with a B, right? We're not using the prefix. So B for butyl, I could start it on this one here, but that would be E for ethyl, or I could start it here, that would be N. So a B beats all of these alphabetically. That's why I'm starting my numbering on this carbon. And I went around clockwise because that puts gives my second substituent the lowest possible number. So that's why I chose to number the chain the way I did, because I needed to put number 1 on the substituent that wins alphabetically. All right, so now I've got my 1 tert-butyl, I've got my 2 ethyl, and I've got my 4,4-methyl. Right, when we put that all together, that's going to be a 4,4-dimethyl. So now let's put the whole name together, remembering what the commas and how the commas and hyphens are used. Okay, so if you recall the template, our parent name was cyclohexane. Now, that was the stem. And all of this stuff here is going to be for our substituents. Now we arrange our substituents alphabetically. Okay, I know this is getting confusing because I said prefixes aren't used alphabetically. All right, but our substituents must go alphabetically in front of the parent stem. So look, the tert-butyl, it goes B, E, then M. So 1 tert-butyl, 2 ethyl, 4,4-dimethyl cyclohexane. And we see that hyphens separate numbers from letters, except for this one here. That one, that actually shouldn't even be there. It doesn't need a tert-butyl. You can leave that. You can leave that out. The hyphens separate the numbers and the letters, and the commas separate numbers from each other. And we put it all together alphabetically in front of the parent stem. Let's look at another example. We want to first find our longest parent chain. So you could have chosen a few different parent chains that had 9 carbons, but the one shown here is the parent chain with the most substituents. So if we identify our substituents now, I see that we've got an ethyl group, we've got a methyl group, a methyl, and an isopropyl. Now we need to number the chain. This one's a little bit easier because I see that my first substituent shows up at the 2 position, versus if I started numbering from the other direction, it would be 1, 2, 3. So that option is out. So I start numbering here because my first substituent gets the lowest possible number. So it looks like I've got a 2-methyl substituent. I've got a 6-methyl substituent. I've got a 5-isopropyl, and I've got a 7-ethyl. All right, so the parent name was nonane. Now we have to put everything out in front, and we're going to arrange this alphabetically. So I begin with the E, okay, 7-ethyl. Remember, hyphens separate letters and numbers. This is my 7-ethyl. And then next alphabetically will be I, and that's a 5-isopropyl. And then we have our methyl groups. So if we have two of the same, notice I use that prefix, that dimethyl. And I'm basically telling my reader that on the 2 and the 6 carbons, I have a methyl group. So I have 2,6-dimethyl nonane. So for the next set of problems, I'd like you to pause the video and give these a try on your own. When you come back, I'll give you the answers. All right, hopefully you were able to give these a shot. Now, first we have to identify the longest parent chain. 1, 2, 3, 4, 5, 6, 7 carbons in a chain. Now you could have, if you started over here, you would have seen that you'd have less substituents. So I start down here because it gives me the carbon chain with the longest chain with the most substituents. Alternatively, you could have also chosen this parent chain, which is identical. Either way, it both gives you an ethyl group. All right, now we have to number the chain. I can start numbering from the left, 1, 2, and I have my first substituent on the 2 position. Or if I start numbering from the right, 1, 2, 3, my first substituent is on a 3. So it looks like that first route is the best. Let's continue with that. 1, 2, 3, 4, 5, 6, 7. And I have a few substituents. I have a 2-methyl. And I have a 3 and a 5-ethyl. All right, so when I put the name together, remember E is going to come before M, and there's 2 ethyl groups. So I have a 3, 5 diethyl, and then we had our 2-methyl, and the parent chain was a heptane. 3,5 diethyl 2-methyl heptane. All right, let's look at the next one. You can number our parent chain. 1, 2, 3, 4, 5. You could have done any number of these. It really didn't matter. I'll show you another possibility. You have a lot of correct answers here. 1, 2, 3, 4, 5, because this is a symmetrical molecule. Let's number it 1, 2, 3, 4, 5. So this is going to be some form of pentane. And now I've got some substituents here. I've got a methyl, and an isopropyl. So that's a 3 isopropyl, a 4-methyl, and a 2-methyl. All right, so I comes before M. Remember, isopropyl is the only prefix that we count alphabetically. So we have a 3 isopropyl, and my methyls, I need to say we have a 2,4-dimethyl, and the parent name was pentane. All right, let's name the next set. If we start numbering here, 1, 2, 3, 4, 5, 6, 7, 8. That gives me the longest chain with the most substituents. And now I could start numbering here 1, 2, 3, or I could start numbering here 1, 2, 3. Now I have substituents. My first substituent shows up to the 3 position. Now I have to go to the second substituent. I could have one at 4, or it would be 4, 5, 6. So our starting from numbering from the left is the correct way to number it. 5, 6, 7, 8, 9 carbons. I've got a 7 methyl. I have a 4 ethyl, and a 3 methyl. Now let's put it all together. E comes before M, so I have a 4 ethyl, 3, 7 dimethyl, nonene. Let's look at our next one. Pretty clear that we have a carbon chain with 1, 2, 3, 4, 6, 7, 8, 9. I probably want to start numbering it here from the right because that puts my first substituent on a 4. So 9 carbons in my longest chain. That's a 4 isopropyl. This is a 5 tert butyl. So B comes before I. So it's going to be a 5 tert butyl, 4 isopropyl nonene. The next set of compounds are going to be the bicyclic alkanes. So a bicyclic compound is simply any alkane that contains 2 fused rings. So we have a double ring system. These are the same exact molecules just drawn in different ways. So this one here gives you a bit of a 3D perspective of what's going on. When we name bicyclic alkanes, we're going to follow 3 steps. Step 1 is we're going to count the total number of carbons. Step 2, we're going to identify the 3 paths connecting the bridgehead atoms, which we'll learn how to identify. And counting the carbons between each path, and we're going to put those in brackets here. So here's our numbers in between brackets, 2, 2, 1, in descending order. In step 3, we put the bicyclo at the beginning of the name. So let's look at our first example. Step 1, let's count the number of carbons in our bicyclic molecule. 1, 2, 3, 4, 5, 6, 7. So that means that I'm dealing with some type of bicyclo something heptane. All right, step 2, we need to identify the bridgeheads and count the number of carbons between each path. So a bridgehead is simply where the two rings meet. So we have two bridgeheads. Now, there will always be three paths connecting the two bridgeheads. We can go around this way. That's one path. We can go around this way. That's another path. We can go up over the top. That would be three. Three paths connecting the bridgeheads. Now what we're going to do is simply count the number of carbons in each path. Do not count the bridgehead. Okay, so we have one carbon, two carbons going around this way. Let's go around to the right. In between the bridgehead atoms, we have one, two carbons. So that's two. If I go up and over the top, I see I have just one carbon in that path. Remember, we are not counting the bridgehead atoms. So one carbon in that path. So I ended up with a 2, 2, and a 1. So in our brackets, we list them in descending order with a period 2, 2, 1. And I just plug that into my name. Put the bicyclo. So we have a bicycloheptane. Bicyclo-2,2,1 heptane. All right, let's take a look at the next couple examples. All right, so we have a fused ring system. We're going to count the number of carbons in the total in the ring system. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's some form of nonane, and because we have two fused rings, it's going to be bicyclo. Now to determine the paths. This is a good one because even though we have to define three paths in our brackets, it doesn't always mean you're going to have carbons in the path. So let's look. Here's our bridgehead atoms. These are the bridgeheads. Okay, so we're going to count the carbons in the path. So there's the bridgeheads. I'll do this with another color. So we have 1, 2, 3 carbons in this path connecting the bridgeheads. 1, 2, 3, 4 going around that way. And the path that directly connects them here has 0 carbons. So if we list them in ascending order, it's 4, 3, 0. So we get bicyclo 4, 3, 0 nonane. In our next example, let's count the total number of carbons. 1, 2, 3, 4, 5, 6, 7. So it's going to be some form of bicycloheptane. And now we have to look at our bridgeheads and count the number of carbons in each path connecting. So the bridgehead is where the two rings are fused. So I've got a path that goes around to the left with 1, 2, 3. We've got a path that goes around to the right with 1, and a path that goes up and over with 1. So I have a 3, 1, 1 that goes in my brackets. So we put the name together, and it's bicyclo 3, 1, 1 heptane. A substituted bicycloalkane. To number them, we start at the bridgehead, and we number the longest chain connectors first. So we number on the longest path first. And without violating rule number 1, we give the substituents the lowest possible numbers. So, for example, if we wanted to name this compound, we would count all the carbons in the bicyclic ring system. Don't count the substituents now, so that's 5, 6, 7, 8, 9. It's going to be some form of bicyclononane. Now I have to number the chain. All right, so remember, we start at one of the bridgehead atoms, and we have to go around the longest chain connector first. So we have to either start here and go that way, or I have to start here and go this way, because this is the longest path I have. If you look at each of the paths, I've got a path with 1, 2, 3, 4, or I've got a path with 1, 2, 3, and then the path in the middle has 0. So I need to start with the longest path. That means I got to count around this side. Now, let's read the rule again. It says to number the parent chain, we're going to start at a bridgehead, number the longest chain connector first, so I know which way I'm going. But now I have to decide what numbering system gives my substituent. You can see that we just have a methyl substituent, the lowest possible number. So I can count 1, 2, 3, 4, 5, 6, 7. Or if I started here, 1, 2, 3, 4, 5, 6, 7, 8, my substituent would have a 9. So a 7-methyl beats a 9-methyl. That's why I began numbering at the bridgehead that I did here. Remember, you always have to start numbering at a bridgehead. You count around the longest chain first, and then you try to give your substituent the lowest possible numbers. All right, let's look at another one. We want to count all the carbons in our bicyclic system. Remember, do not count the substituents 1, 2, 3, 4, 5, 6, 7, 8. All right, and now I see that all of my chain connectors, that's 2, 2, I have 2 carbons in each of the paths, right? 1, 2. Connecting the bridgeheads, 1, 2, 1, 2. All right, so really, it doesn't matter what path I start going around. However, what does matter is the bridgehead that I start at. So if I start here, I get 1, 2, 3, 4, 5, 6. All right, and I have my substituent out of 1. Or if I started on the other bridgehead, I'd have a 1, 2, 3, 4. My isopropyl will be at the 4. So 1 isopropyl beats a 4 isopropyl. I think it's pretty clear how we number this one. And our next example, we want to count the number of carbons in the bicyclic system. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be some form of bicycloalkane. I've got a methyl. Now I just have to decide what the substituent number will be. So let's take a look. If I start numbering at, remember I have to start at one of the bridgeheads, one of these bridgeheads, okay, and I have to go around the longest path first. So I definitely have to either start that way or count around that way, because that's the longest path. If I count around starting here at this carbon, I get 1, 2, 3, 4, 5, 6. So my methyl is on a 6. But if I started at the other bridgehead counting around the longest path, I'd have a 1, 2, 3, 4, 5, 6, 7. So a 6-methyl beats a 7-methyl. Therefore, I number in this fashion. All right, I'd like you to pause the video and give these a try. These will not have any substituents on them. You just have to give it the basic bicyclic name. okay? And when you come back, I'll give you the answers. All right, hopefully you've been able to give these a shot. Let's begin with the first one. We want to we want to actually count all of the carbons in the bicyclic system. So that's 4, 5, 6, 7, 8, 9, 10. So this is going to be some form of bicyclo something, 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 decane. All right, now remember we have to count the number of carbons in the path. So I have a path going around to the right with 2. I have a path going around to the left that has 4, and a path going up and over. Remember, I'm trying to counting the carbons connecting the bridgeheads with 2. So this is a 4, 4, 2 system, and we would call this bicyclo 442 decane. In our next example, we can count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be some form of bicyclo something, 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 nonane. All right, well now let's count the carbons in between each of the bridgehead paths because we have 3 paths that we have to consider. That one's got 2, that one's got 3, and this one's got, here, that one's got 2. Just list them in descending order, 3, 2, 2. So we have bicyclo 322 nonane. In our final example here, we're going to count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means I'm dealing with some type of bicyclo something, 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 decane. Now let's find our bridgeheads. We're going to count the carbons connecting them in each path. So if we go around to the left, there are 4 carbons. If we go around to the right, there are 4. And if I go right from bridgehead to bridgehead, there are 0 carbons in that path. So I've got a 4, 4, 0. We call this bicyclo 440 decane. All right, and that concludes the lecture on naming alkanes. In our next set of notes, we're going to look at naming the rest of the type of molecules, alkenes, alkynes, and then we'll begin looking at names for different functional groups in molecules.